Koto, it's Mrs. Goodson here. This video is about periodic trends, which there are three parts to stating the trends from the periodic table. The first part is atomic and ionic radar, which was covered in part 1. The second part is ionization energy, and that's what I'm going to cover in this video. So the first ionization energy is the minimum energy required to remove one electron from each atom in a mole of atoms in the gaseous state. So it's an amount of energy per mole. And so the unit is here, kilojoules per mole. So this can be written as the general equation. So if you have an element in its gaseous state, and you want to remove one electron, you're going to end up with an ion, so it's ionization. And then the change in energy is always a positive value, so we'll just put X, we don't know what it is for this general statement, and the unit is kilojoules per mole. So this process is always endothermic. That means it's going to absorb energy from its surroundings, because the energy is required to overcome the electrostatic attraction between the nucleus, which is positive, and the valence electrons, which are negative. So there's that is the attraction holding the atom together. And so you need to add energy from the surroundings to remove that electron. So the first ionization energy is the first electron, and then the second ionization energy would be removing the second electron, and so on. Okay, so for level 3, you need to know the basic trends. So as you go down a group in the periodic table, remember a group is a column. So for example, if you go from lithium to sodium to potassium, the ionization energy decrease. This means it's going to need less energy to remove that outer electron. And this table shows the first ionization energies from everything from hydrogen to krypton and rubidium. So then across a period, or across a row, so if you go from lithium to beryllium to boron, the ionization energy increases. So if you see on this graph, so lithium, this is atomic number increasing. So lithium, the general trend as we go across a row is for the ionization energies to increase. As you go across the row, you need, for each element, you need more energy to remove the outer electron. So you need to know these trends. This would be an achieved level learning outcome. And then to explain the trends as more merit excellence. So the first trend is as you go down a group. So for example, lithium, sodium, potassium in the first group, but this applies to all the groups. So as you go down a group, the ionization energies decrease. Now, if you have a look at the SPD notation over here for these elements, you can see that the last electron, valence electron, is in a subshell by itself. Okay, so it's actually in a whole shell by itself. So in lithium, the valence electrons are further away from the nucleus. So lithium has 2 electron shells, sodium has 3 electron shells, and potassium has up to 4. So we've got 4s over here, 4 electron shells. So this electron is much further away from the nucleus compared with in lithium, where it's much closer. So there's a whole lot of electrons in the way. These inner electrons, we can say that they shield the outer electron. And we can also say that they provide electron-electron repulsion. So that decreases the electrostatic attraction between the nucleus and the valence electron, and therefore less energy is needed. So potassium is going to have a smaller ionization energy compared with sodium and then compared with lithium. So as you go down a group, the ionization energies decrease, and this is the explanation for that. Now, the other trend was that as you go across a period, so if you go from beryllium to boron to carbon, the ionization energies increase. And so the first step is you'd write the SPD notation. So you can see as you add an extra electron. So you've got boron, carbon, nitrogen. These electrons are going into the 2p suborbital, and the ionization energies increase as you go from boron to carbon to nitrogen. But then you need to explain why. Why does it increase? As atomic number increases, there are more protons in the nucleus and electrons are being added to the same level. So in this case, adding to 2p, just for this example. So there's no additional shielding. The inner electrons, or these core electrons, are not changing. So the shielding doesn't change as you go from boron to carbon to nitrogen. What is changing is that there's more protons, and as a result, there is a stronger electrostatic attraction between the nucleus and the valence electrons. And so as you go from boron to carbon to nitrogen, you're going to need more energy to remove the electron. So as you go across a period, ionization energies increase. Okay, now there's some smaller things going on in this graph, so you can see the big trends. So as you go across a period, the ionization energy increases. But there's a few little dips and things that we can explain using subshells. So the graph of ionization energy provides evidence of subshells. And there's two main points here. So going from beryllium to boron and magnesium to aluminium, there is a small little decrease in ionization energy, which goes against the overall trend across the row. So why is this? Boron and aluminium both have its outer electron in a new p subshell. So let's have a look. So we've got beryllium is 1s2, 2s2. Boron is 1s2, 2s2, 2p1. So this outer electron is in 2p1, even though it's still in the second shell. So it's actually easier for this, it's quite easy for this boron to lose this one electron. And so that's why there's this little kink in the trend. Boron and this happens for aluminium as well, further along. Boron and aluminium both have its outermost electron in a new p subshell, which is further from the nucleus than the s shell. This means that the attractive force between the nucleus and this valence electron is smaller, and so the energy needed to remove this electron is less. So these little kinks here are evidence of the p shell. Now then we want to look at the next little kink. So between group 15 and group 16 elements, for example, between nitrogen and oxygen, and between phosphorus and sulfur. So this is because group 15 elements have 3 unpaired electrons in separate orbitals in the p subshell. So we can see this if we draw the box diagram for nitrogen. Each p electron goes into a different subshell, separate orbitals. It was Hund's rule that we filled them up, 1 in each subshell. Compared with oxygen, which has 2 in the first one. So it's got these, and there's 2 unpaired ones. So this nitrogen one is actually a little bit more stable than the oxygen. So oxygen needs less energy to lose 1 electron compared with nitrogen, which is a bit more stable. So it provides a bit of a kink in our trend. It goes against the trend that when you go across a row or a period that is increasing, actually decreases when you go from nitrogen to oxygen, and it decreases when you go from phosphorus to sulfur. And when you look at how the arrangement of the electrons, you can use that to explain that nitrogen has got the stability from having 1 electron in each orbital. So these paired electrons have slightly greater electron-electron repulsion. So the oxygen, this one's got slightly greater electron-electron repulsion, and slightly less energy is needed to remove 1 of these paired electrons. And this happens for phosphorus and sulfur as well. So so far we've been talking about the first ionization energy, and then you'd need to add even more energy to remove the second electron and the third electron. The second electron is a little closer to the nucleus, therefore stronger electrostatic attraction, which will require more energy to remove. And this is just a graph of the ionization energy of aluminium. And you can see that as you remove, so that we remove the 3p electron, then we remove the 3s2 electrons, and you just need more and more energy to remove the electrons. Okay, this is an example exam question from 2018. So this question actually brings together atomic radius and ionization energy. So the question asks to explain the factors influencing the trends in first ionization energy and atomic radius across the second period, which is the second row of the periodic table. In your answer, you should describe the trends in both first ionization energy and atomic radius across the second period. Explain the factors influencing the trends in first ionization energy and atomic radius across the second period, and relate the trend in first ionization energy to the trend in atomic radius. Okay, so this is the model answer that was given for the assessment. Okay, let's break it down. So the first ionization energy increases across the second period. Okay, so that states the trend. The atomic radius decreases across the second period. Okay, this is also stating the trend. So if you do that, it's going to be achieved. All right, so you're looking at achieved grades for those ones. All right, so we state the trend, and then you need to explain each trend. All right, so focusing on ionization energy first. There is an increase in the number of protons, therefore the nuclear charge of the nucleus increases. As the electrons are added to the same energy level across the second period, the electrostatic attraction increases. So you've talked about increase in protons, the same energy level, link it to the electrostatic force, and link it to more or less energy. Also for atomic radius, you need to explain the trend, break it down. There's an increase in protons as you go across the second row. Electrons are added to the same energy level, link it to the electrostatic force, link it to the distance between the nucleus and the valence electrons. And then for excellence, you have to add this bit here, which is where you compare the two trends. So as the ionization energy increases, the atomic radius decreases as you go along the second period. The same factor of increased nuclear charge due to more protons and electrons on the same energy level means the decreased radius but increased stronger attractive forces, meaning more energy is needed to remove the outermost electron. So I will post this PowerPoint for you to look at, and I